Hey, it's Dr. J. Today we're going to be completing the catalog of functions. So these are 6 of my favorite functions that we will be using as we discuss the transformations of functions. This is by no means an exhaustive or comprehensive list of every type of function. There are hundreds, if not thousands, of different types of functions, but I've selected 6 that appear quite frequently in a college algebra course. So in this video, I'm just going to walk you through how to complete a blank catalog, and then you can use this to help you as we move through the terminology and the transformation vocabulary of functions. You might see me refer to it in my future videos. So every function has 2 forms. We have the function form. This one is f of x. I'm going to use a combination of the whiteboard and the paper. So this is f of x is the absolute value of x. I don't know if that's coming across clean. So this is what we call the absolute value function. The key feature is the absolute value bars, which I have written here. And that's the distinguishing feature that places it into its family. So we call this a family, and this family is the absolute value family. All right, so that's the name of its family. Essentially, any function that contains the absolute value bars will be a member of this family. It can also be written in y equals form, which is usually the way I write it when I'm working with it. I'll say y is equal to the absolute value of x. And so our input is going to be x, and then our output is going to be y. All right. And so we have a table here, an input-output table, that we will use this equation to complete the inputs and outputs. Now you're free to pick any x's you like as inputs. However, since this is the first one, I recommend using the inputs that I am pre-designating. We call this a sample set of inputs. All right. X can be any real number. So you are free to plug in any real number. All right. Now, I tell you that you're free to plug in any real number because you can. You don't have to use the 5 inputs that I've pre-designated. You could use other inputs. You could plug in -3, or -4, 5, 12, 106. You can even plug in fractions, and I might have to do that in a future example. But in this one, I'm sticking with a very simple set. All right, -2 is my first input. So let's do that. -2. So we're plugging in -2 for x. That's going to be our input. All right, and then the number that comes out is the y value. So the absolute value of -2, the absolute value of -2 is 2. I don't need the ruler right now. So over here on my input-output table, I've plugged in -2 as an input, and I got my output of 2, and so I'll complete my table, -2, 2. I know I made a real big deal about that first one. As we move through the examples, I'll probably go a little bit faster, but I just want to make sure that as I'm doing this, you know what the heck I'm doing. All right, I'm going to use this over again. My next input is -1. So I'm going to plug in x equals -1 as my input. So in other words, y is the absolute value of -1, and the absolute value of -1 is +1. So on my table here, if x is -1, y is +1. So on and so forth. We're going to keep plugging in values for x. My next input will be 0. Plugging in 0 for my input. 0 is a very special number. It's neither negative nor positive. So when you take the absolute value of 0, kind of looks like LOL, it is still 0. There you go. We could do the next two mentally, if you like. Sort of the standard way to do it. When the input is a negative number, I like to show the math. When the input is a positive number, it's really not necessary to show the math. The absolute value of 1 would be 1, and the absolute value of 2 would be 2. So you'll notice something about the outputs. The y values are always positive. So we have a blank grid here, a Cartesian plane, and we're going to draw the graph. Because the outputs are always positive, when I do my graph, none of the y values will be negative. They will all be positive numbers. So I'm going to appropriately place my axes right down the middle. So this is my x-axis. This is my y-axis. Inputs are x. Outputs are y. I don't need this anymore. Okay. And we're going to plot the center row first. This is called the 0, 0 vertex. 0, 0. I need a better pen. Let's see if I can find a better pen. I found a better pen. So 0, 0 is called the vertex. All right, it's very important that we plot this point first. All right. Now, again, I won't know whether you plotted it first if you're doing it on paper, right? However, the computer, you're going to be doing this with your mouse, it'll be very important that you click on that point first. Then I'm going to plot 1, 1. Then I'm going to plot 2, 2. It's probably not a bad idea to mark these off on your paper. All right. And then don't forget the negatives. If x is -1, y is +1. So we have a point here, -1 and +1. And if x is -2, y is +2. And this is the graph of the absolute value function. Even though we only plotted 5 points, the graph has infinitely many points in the relation. So the graph goes off to infinity. You can either go right off the edge of the screen, or you can use little arrow tips like this to indicate that it continues on to infinity. And there you have it, the absolute value function. And an important vocabulary word here, this center point here where it changes its direction, is called the vertex. All right, next we're going to look at the shape of the graph, and we're going to answer the domain and the range. You might want to zoom in on this a little bit if you can. This is the domain. In formal set notation, it's the set of all x such that x is an element of the real numbers. And sometimes we write real numbers with a fancy double-lined R for real numbers. It's a mathematician's way of saying real numbers. I've got my camera zoomed in, so I don't have a lot of room to write here. So this is what we call the double barred R, which means real numbers. If you don't write it with the 2 bars, I still know what it means. You can just type a capital R if you're typing. Now the range, remember, is the outputs. So it's the set of all Y. Now be careful. Y is not all real numbers. Look over here at the Y values and you'll notice that 0 is the smallest Y value. So Y is greater than or equal to 0. So that's what we call the formal set notation for the domain and the range. We have a more sleek or slick modern notation called interval notation. I think of the formal set notation as very proper, very old-fashioned. And then we've got a sort of a 20th, or now it's the 21st century version of the answer. Negative infinity, comma, infinity with open parentheses is the domain. We talked about that when we were solving inequalities, greater than and less than and such. And then for the range, again, back to the inequality, greater than or equal to 0. That's how you say greater than or equal to 0. And it has no boundary. It goes all the way up to positive infinity. Yeah, so the Y values open up to positive infinity. So there you have it, the absolute value function. All right, now that you've seen the exercise and you've seen how we produce these, maybe I can pick up the pace a little bit and go through a few. But if they get tricky, I'll slow down and show more detail if necessary. So there you have it, the absolute value. There's the domain and range. There's the graph. Sometimes we label the vertex with a 0. I didn't really have enough room to put a 0 there. I felt that it would, clutter it up, so I omitted it. It's implied that that point is the origin, which is 0, 0. All right. So moving right along, the second member of our catalog is called the quadratic. It's also known as a square, but the formal name is quadratic. F of x is equal to x squared. The distinguishing feature is that it has parentheses squared. So when I do my evaluations, when I plug in my x, I will remove the letter x and I'll use parentheses to figure out what my output is. Remember, the output is y. All right, so that's the key feature, parentheses squared. And so you'll see that in the catalog here in the next to the family name. I don't know if that's helping, but might be getting a little blurry. The key feature here is the parentheses squared. I have my focus set to focus on the board, so it looks a little better here. All right, so let's get going. Let's plug in some x's. All right, now remember, I can pick any x's I like, but I'm still going to use the same x's. You'll find that I'm a creature of habit when it comes to plugging in values. I often, but not always, but I very often use the same 5 numbers every time. -2, -1, 0, 1, and 2. unless there's a reason why I want to use different numbers, I usually stick with those. Okay. And again, you are free to pick other numbers if you like. It really won't matter. You'll get the same result. But your graph may not look identical to mine unless you follow the pattern that I'm using. But you can plug in, negative 43 if you want. You might not like the result, but it would still be true, assuming you use the function correctly. All right, so let's plug in our first input is negative 2. That's our first input. And then our output will be y equals 4. Yeah, negative 2 squared is 4. So on my table here, the y value will be 4. You could probably do all of these mentally, right? I sure hope so. However, I'm going to do at least the first couple by hand. The next input is negative 1. Negative 1 squared is positive 1. And there you go. The y value is 1. Let's do the rest of them mentally. Okay, so if you plugged in 0 for x, maybe I'll do it here. You're going to get 0 for y. I said we're going to do it mentally. I just mean I'm not using a calculator. If I plugged in 1 for x, again, I would get 1 for y. It's very similar to the absolute value. The key difference is this one is squaring the number. And so when you square 2, you again get 4. And so you'll notice a similarity here with the values. All right, so again, that's completing the table of values. Again, this is the sample set that I chose. You could certainly use other x's. If you used another x, you might get an additional point on your graph. If we find that useful, I may do that. Okay, so again, you want to put the x and y axes appropriately. For this one, I like to put my x-axis just a little bit down. Not exactly in the middle. It's an artistic choice. I just find that the graph looks a little bit better. You could put the x-axis all the way at the bottom if you liked, but I like to show the empty quadrants. So quadrant 3 and quadrant 4 will remain empty. Again, you want to start with the vertex. All right, 0, 0 is the vertex. So if you were doing this with your mouse on your homework, you would click that point first, 0, 0. And then I'm just going to go through the list here. So I've got negative 2 and 4. Put a dot right there. Negative 1 and 1. I could label that as 1 just to make it absolutely clear. But unless you're specifying a different scale, assume that each block is 1 unit. There are some examples where I like to do a slightly different scale so that it's more clear, so that these numbers aren't so clustered together. So my next point is 1, 1. And then my final point is 2, 4. Right. Now I'm going to draw this by making a U shape down here at the vertex. I want it to look curved. I don't want it to look like the absolute value function. Right. Just a quick review. The absolute value function has the shape of a V. The quadratic function has the shape of a U. So this is what you would get if you only considered the numbers between -2 and 2, the x values between -2 and 2. But as I mentioned earlier, you could plot additional points. They don't have to be in your table unless you want to add them to your table. But suppose I did a 3 for x. Right? And again, I don't have any room in my table to put it in there, but I could certainly put it in my mind. What would 3 squared be? Well, 3 times 3 would be 9. So this point, even though I didn't include it in my table, it still exists in the plane up here at 9. And so the graph continues all the way to infinity. Right? So sometimes adding 1 or 2 additional points helps you understand that the relation is infinite. There are infinitely many possibilities. All right? So you don't just want to stop at 4. And again, on this side, it would also go up to 9. We call that symmetry, right? It has a reflectional symmetry across the y-axis there. So that's a good graph of a quadratic function. So let's go down here and do the domain and range. Again, the domain is the set of all x such that x is an element of the real numbers. This little e symbol here is an epsilon. I'm not sure if I mentioned that earlier. This symbol here is the Greek letter E. It's the Greek letter E, which is known as epsilon. And then I already mentioned this fancy double-barred R means real numbers. So this means x can be any real number, or x is any real number, or x is an element of the set of all real numbers. Those all mean the same thing. You've probably gotten used to that about my course, is that I often say the same thing several different ways. The range, on the other hand, almost used the wrong letter. The range must be y values. And again, just like in the previous example, that's a terrible brace there. The set of all y such that y is greater than or equal to 0. Sorry about that. That one could have been done better. Let me try that again. There we go. Oops. So again, notice here on the graph, all of the y values are greater than or equal to 0. And again, a simpler notation, or at least a more streamlined notation, is the interval notation, -infinity, comma, infinity. And then for range, bracket 0, comma, infinity, which means greater than or equal to 0. All right, so there you have it, the quadratic function. All right, moving right along. We're almost halfway there. Well, we're 1/3 of the way done with the worksheet. Our next function, the square root. Sometimes it's written this way with an index of 2. We call that the index. It does not have to be there. If you don't see it, it's an invisible. It's an invisible 2. Some calculators will show it like this, and some won't. doesn't hurt to have it though. In the catalog, I omitted it. So it's implied to be a 2 by the symbol square root, also known as a radical. A radical of index 2. So radical index invisible 2. To really make it invisible, I like to erase it. Okay. Now, this one's special. All right. This is one that's very special. We want to avoid imaginary numbers. All right. We want only real numbers. So we don't want this to happen. All right. And you may have already learned about imaginary numbers. I may have already covered them in this course, depending on when you're watching this video. And so we know that this is an imaginary number, right? We know what it is. We know that this is equal to I. But for the purposes of a function, we are prohibiting imaginary numbers. And so what that means is in our table of values, we're not going to start with -2 and -1. We're going to start with 0. That's going to be our initial x value, 0. And that will prevent this from happening. All right, so let's go ahead and do it. If we input 0, what do we get out? The output would be the square root of 0. You don't need a calculator for that. The square root of 0 is equal to 0. And we're going to follow the same procedure that we did in the last example. We're going to plug in 1 next. Again, you don't need a calculator for 1. Square root of 1 is 1. So my input is 1 and my output is 1. Okay. Now watch this. I'm going to skip 2 and 3, and I'm going to go to 4. All right. And it's really because of my grid, right? My grid really does not work well with decimals. Although I could, say, this is 0.1, 0.2, 0.3. I could make a decimal grid if I really wanted to, but it's not necessary, right? And it may become necessary in the future to use decimals or fractions. But I'm going to try to avoid them. So in order to avoid decimals and fractions, my next input will be 4. And that way, when I take the square root of 4 becomes 2. And in my table here, I inputted 4, and my output is 2. Now, if you don't have the foresight, to know to do that, and you plug in 2 or 3 or 5 or 6, you will just get a decimal output, and then you'll look at your grid and you'll be like, you could possibly find a way to fit a decimal onto this. It is possible, but I'd like to avoid it unless it's necessary. All right, so I only use decimals in case of emergency, when I have no other alternative. So having said that, my next input is going to be 9 for x. You see what I'm doing here? You probably can imagine why I'm picking 9 to be the next input, because the square root of 9 is 3. Right? That gives me a nice output of 3. Right? It also shows you the invisible index. Right? Again, you've seen me draw these clouds before. The clouds are what you're thinking when you do a mathematical operation. I don't know if you see the little face there, but there's my brain thinking about math, right? And so I'm thinking 3 squared is equal to 9, right? So x is 9. and the y is 3. Yeah. You don't actually see the little index. The index is invisible because it's the square root. So because 3 squared is 9, we say the square root of 9 is 3. All right. Yeah, you're all college algebra students. You've seen that at some point in this course already. So I think I'm over-explaining a little bit, but you know, that's what I do, right? I mean, that's why I'm here. Okay, and then my final point will be 16 for an input, and you'll see that my output is 4. Now I got to be really careful with my grid here because I want to make sure 16 fits. So I'm actually going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I'm going to count to make sure I have 16 boxes. So there's my x-axis, and I'm going to put my y-axis way over here. Because I want to fit as many of these points as I possibly can. So this is 0. This is 1, 2, 3, 4. So I'm just marking off my x's. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I barely made it. If for some reason on a homework problem or, you know, a quiz or a test, there isn't enough room to go to 16, that's forgivable. Yeah. But, you know, I went through all the trouble of setting up the camera and making this video. I want to get them all on there, okay? In your case, if you only have enough room to go to 9, then just go to 9. It'll be fine. All right. And then we're going to plot our first point at 0, 0. Yeah, 0, 0. And then 1, 1, right there, 1, 1. And then 4, 2, 4, 2. X is 4, Y is 2. 9, 3. X is 9, Y is 3, right there. And then 16 and 4. And I like to turn it like this when I'm drawing and curve it like this so it does not look like a straight line. I find that if I do it side to side, I end up drawing a straight line. So I just kind of curve it like this. Gives me a nice arc called the square root function. Before I do the domain and range, I just want to make a comment about the 0, 0 point. It's not called a vertex. It's called the terminal point. So we call this point at the top the first point we plotted. It's also known as the initial value because it was the first thing I did. But the proper name for it is the terminal point. The graph is terminating at that point. That's important because I don't want your mouse, if you're doing this with a mouse, or I don't want your pen, if you're doing it with a pen, to go beyond that point. It is terminal, right? So the graph ends at that point. If you're an optimist, you can think of the graph as beginning at that point. That's when I started this example, I called it the initial value, right? Well, if you think about the word terminal, it means both a beginning and an end, right? Think about the airport, right? When you go to get on a plane, right? So you go to the airport, you get on the plane in a place called the terminal, right? Terminal 12 or terminal 4B or whatever, right? So you go to your terminal to get on the plane. But you might notice while you're waiting to get on your plane, other people are getting off of their plane. So for those people, the people that are getting off the plane, it's the end, right? It's their destination. For you, it's the beginning. So a terminal could be either a beginning or an end. Ooh, that's some deep philosophy there. All right, so now we're going to do the domain and the range, the formal set notation, the set of all x. Notice that my terminal point is 0, so x is greater than or equal to 0. And notice the range is the same, but we use a different variable. The set of all y such that y is greater than or equal to 0. So that is your formal set notation for domain and range. The interval notation is square bracket, 0, infinity, and the same for the range. Notice with interval notation, you don't indicate the letter x or y. X and y are implied by the name domain and range. So if I say domain, it's implied that this means x. And range, it's implied that this means y. In the formal set notation, nothing is implied, right? It's formal. You have to clearly state everything. You have to state what the variable is, state the inequality that it satisfies. So there you have it, folks. The catalog of functions. Oh, I forgot to put the family name here. It's called the square root family. It has another name. It's the radical of index 2 family. But nobody wants to write radical of index 2 family. So we just say square root. There are other radicals. So that's why the index is important. This is a square root, radical of index 2. And there you have it. Okay. Moving right along. We are now halfway done. The next function in our catalog is the cube or the cubic. The cubic. I would also accept the cube, but I'm going to go with cubic. So the key feature is the parentheses cubed. That's the defining feature of the family here. I put it next to the word family so that you know that everybody with this is part of the cubic family. And again, you don't see the parentheses in the original problem, but they're there. Yeah, the x is surrounded by a set of parentheses, even if you don't see them. They're implied. We're going to remove the x, and we're going to plug in numbers for x, just like we've been doing for all of these. I'm going to go back to my traditional inputs, -2, -1, 0, 1, and 2. Same inputs that I used for its cousin, the quadratic. However, the outputs are not going to be the same. The inputs will be the same. You can't pick the y's and the x's at the same time. You can pick one or the other. You could pick y and then figure out what x would be. It's always easier to pick what goes in and then let the function determine the output. So your output is -2 times -2 times -2. And so that's -8. That's your output. Your input was -2. Your output is -8. So -8. So on and so forth. Complete the rest of the values. While I was preparing for this video, I experimented with the time-lapse video. This would have been a great time to speed up the camera. Unfortunately, it was very difficult, if not impossible, to go from talking normal to speeding it up in time-lapse. I could do one or the other, so I had to make a decision. Do I want the whole video in time-lapse? Also, when you do time-lapse, the audio is disabled. But if you're watching this on YouTube, you can just watch it at fast speed here. So you have -1 times -1 times -1. Pretend like I'm doing this in time-lapse video and I'm going really, really fast like this, and you won't be able to hear me talk. Although I think you can probably hear me. Can you? I've never watched the videos in time-lapse. The input was -1 and the output is also -1. So you get -1, -1. All right. I don't think I need to do the rest of these on the board. I think you can do them all yourself. 0. 0 times 0 times 0 is 0. You see where the time-lapse would have come in handy? 1. By the time I write it out, you'll already have the answer. 1 times 1 times 1 is still just 1. And so input, output. And finally, 2. 2 times 2 times 2 is 8. I like to write it out so that you don't accidentally put 6. I have had students go 2 to the 3rd. They'll skip all of this and they'll write =6. It happens all the time. If you're in my online class, I probably wouldn't see you writing it, but I would see you typing 6. And yeah, it's there. Even if you redo the problem, I still see that you did it once. I can see every keystroke you make, believe it or not. It's kind of creepy. Yeah. And how long you spent working on that problem too. So I get two things on my end. I can see how long you played around with it and how many different times you attempted it. But let's get on with the rest of the example. So that's the cubic. These are our inputs and outputs. I'm going to draw the graph now. For this one, I'm going to go back to kind of like I did at the beginning. I'm just going to put the grid kind of right down the middle here. I'm not going to bother to count, just kind of eyeball what you think the middle would be. I have eyeballed it and regretted not counting, but let's see. I think I'm pretty good. And again, we're going to start with the 0, 0 as our initial point. 0, 0. And then I'm going to go in either direction. You can either, so these points, these negatives will be on the left, lower quadrant 3, and the positives will be on the right, upper quadrant 1. Let's do quadrant 1 first. So we got 1 and 1, 2 and 8. 2 and 8. Don't connect them yet. Get all your dots down first. These negatives will be down here in quadrant 3. So -1 and -1 right there. And then 2, 3, 4, 5, 6, 7, -8 and -2 down here. These numbers are kind of crunched together in there. And then watch how I do this. I'm going to connect the middle dots first. And then I'm going to go up here. And then I'm going to go down here. You could try starting at the bottom and getting through all 5 dots. It's not easy, but it's not impossible either. And there you go. the cubic. So take a minute to get that down. We'll move on to the domain and range. This is a free answer. You've heard of me giving free answers before. All four answers are the same. You do have to be careful with the range. In formal set, you got to use y. But all of these answers are the same. They are all real numbers. All real numbers, all real numbers, all real numbers, all real numbers. And the only difference is in the formal set notation, domain and range have to have the appropriate letter. So domain is x, range is y. There you go. There's your free answer. Negative infinity to infinity. You don't have to calculate it. You just know that it's there by looking at the graph. Look, y goes up to positive infinity forever and ever. X goes to the right to positive infinity. Now that might not be obvious because you got all this blank spot here, but if you went over to say 3, 4, 5, 6, 7, 8, you might go, well, there's no point here at 8, right? Well, there is a point. It's just what we call out of bounds, right? It would be 8 times 8 times 8. Being a math teacher, I feel like I should know that off the top of my head. Eight to the third power, it would be 512. Oh, I feel silly for not already knowing that. So there is a point here. It's just so far out of bounds that you can't see it. It's at 512. And there's another point at 9, and another point at 10, and 11, and 12. So this graph is infinite in both directions, negative infinity and positive infinity. And then I'm going to teach you a new word for the cubic. We don't call 0, 0 the vertex. No, we don't call it the vertex. We don't call it the terminal point. We call it the inflection point. It's called the inflection point. So this point right here, 0, 0, is what we call inflection, or the point of inflection. The definition of an inflection point is not important today. Just, it's that thing. It's where it's bending. The proper definition requires the definition of concavity, and we haven't talked about concavity, but essentially you can see it's changing concavity. Right? This is concave down, and then it's concave up, and at that moment it's changing its concavity, or in terms of language, it's changing its tone. Its tone is changing. That's the inflection, like the inflection in your voice. So there you have it. El cubo, the cubic. Well, we talked about square roots, so we've got another one. A radical of index 3 is called the cube root. So this is the cube root function. Now this time the index is never invisible. Yeah, we wouldn't do that to you. We wouldn't say, sometimes it's an invisible 2 and other times it's an invisible 3. That would be cruel and unusual, and so we will not do that. So this is the little cube, or the cube root. All right. Now remember, a cube root is the inverse, or if I haven't defined inverse in this course yet, you can just think of it as the reverse, We are reversing the direction of the operation. All right, so we're going to be plugging in -8 and not -2. We're going to be plugging in what we used to have as an output. So it's not a bad idea when you're doing the cube root to have this list available, the one we just did, and all of your y's from the cubic are going to become your x's for the cube root. And if you don't remember to do that, you can just use trial and error. Just try different numbers for x. Right? I mean, you're allowed to pick any x you like. And again, you might not like what happens, but I mean, you're certainly allowed to try, right? And you will find through trial and error that these are probably the best choices. All right, so let's go ahead and do it. We're going to plug in -8. All right, and then our output is going to be -2. Our input was -8, and our output is -2. So on my sheet here, my output is -2. There you go. Kind of line it up like that. All right, and let's finish the rest of these. If my input was -1, my output would also be -1. So -1. This is where the time lapse would come in handy. If my input was 0, my output would be 0. So I'd have 0, 0. If my input was -1, oh, sorry, +1. I already did -1. If my input was +1, then my output would also be +1. And then finally, if my input was 8, input was 8, the output would be 2. So my last row here is 8, 2. Sorry, that 8 looks funny, but it's an 8. It's an 8 and a 2. Kind of looks like a G from my angle. Okay, ready to graph? All right, whether you're ready or not, we're doing it. So just take your grid. Again, just kind of eyeball the middle. Doesn't have to be perfect. Just try to get somewhere down the middle. You could count and put it exactly in the middle if you like. 1, 2, 3, 4, 5, 6, 7, 8. All right, I counted to make sure. All right. Again, plot 0, 0 first. That's your initial value. Even though it wasn't the first one I calculated, it's the first point when you're doing it with a mouse. All right. When you're doing it on paper, it really doesn't have to be first, but I'm sort of modeling the way you'll do it with your mouse. You'll click right there first. All right. I don't know if I mentioned this earlier, but once you've clicked the first point, it's going to automatically start creating a graph like as quickly as you can move your hand. Then you just have to stick down one more point. I'm going to stick down all 5 points. So I've got 1, 1, 2, 3, 4, 5, 6, 7, 8, and 2 right there. And then for my negatives, I've got -1 and -1. And then 2, 3, 4, 5, 6, 7, -8 and -2 over here. And I like to do the middle part first, kind of draw like an S shape, and then try to connect the other dots. And again, I said this before and I'll say it again. When you're using the computer, it'll be a little bit easier because as soon as you click on that first dot, the computer will know that you're graphing, assuming that you are using the right function. You got to make sure you choose the right. I got all 6 functions laid out for you. So pick the right one, and then when you click it, it'll go, oh, he or she or they are trying to draw a cube root function, and then all you have to do is click one more time and it'll finish it for you. And these other points will just be kind of included in the process, even if you didn't click, all 5 dots. On paper, it's a good idea to do all 5 dots. So since this is a paper handout, go ahead and plot all 5 of them. And then much like the cubic, the cube root, you get a free answer for the domain and range. Set of all x such that x is an element of the real numbers. Range, the set of all y such that y is an element of the real numbers. Free answer. Again, free if you know it, right? If you don't know it, well, then nothing's free. And then for the interval notation, negative infinity, comma, infinity with open parentheses, or simply parentheses. I like to say the word open. It means that you're not actually including infinity and negative infinity. You're approaching them. That's what the arrow means. You're approaching positive infinity, or you're approaching negative infinity, but you'll never get there. You just keep running and running. All right, there you go. That's your catalog of functions, the cube root, for your enjoyment. Well, we got one more. My goal was to get this in an hour. I think I might go over a little bit, but we'll try to get this last one done. So here is your 6th and final function in this version of the catalog. Again, there are larger catalogs that contain more functions. I'm keeping this one to the ones that I find the most useful in this course. So this is called the reciprocal function. Notice the x is in the denominator. So 1 over anything, any input, is called the reciprocal of that input. All right. This one's a little weird. You'll notice that the table has 7 rows. So the key feature of a reciprocal function is that y is equal to 1 over blank, and that blank is again where you're going to put your inputs. So that's your identifying family feature. So any function in this family will have that 1 over a blank set of parentheses. And you may not always see the parentheses, but if you don't see them, they're occupied here in the denominator with the blank set of parentheses. All right, again, time lapse might be useful here, but I'm going to go 1 point at a time. And because there are 7 rows, I'm going to do -2, -1, -1/2, 0, 1/2, 1, and 2. I'm writing -1/2. You can also write it as a decimal if that fits better. I kind of regret not doing a decimal because that's pretty hard to read because I'm using a pen. Honestly, I tried this video with a pencil and the camera wasn't picking it up very well, so I had to switch to pen. If you're doing this at home, use a pen at your own risk because you risk this happening where the fractions look pretty bad. I might change my mind in the middle of this example and switch to decimal notation instead of fraction notation. All right, so let's go ahead and complete the table. Let's start with our first input. Our first input is -2. And so then the output, you can use a calculator if you like. You don't have to, though. I think you can do these by hand if I could write it. And I'm switching to decimal notation because I find that it's a little easier to write. If you plug in -2, your output will be -0.5. 0.5. And again, it's kind of messy because I'm doing it with a pen, but I think you can bear with me, tolerate me for another minute or two. And let's just go down the list. The next input is -1. It's my next input. And you don't need a calculator for that. 1 divided by -1 is -1. My next input, -1/2. Yeah. Or you could use -0.5 as an input. You're going to get -2 as an output. All right. And I like to show the steps for that because I don't know who's watching this video. When you divide 1 divided by -1/2, you get 1 times -2/1, which is 1 times -2 divided by 1. You see that? There we go. 1 times -2 is -2 divided by 1. And that's just equal to -2. So that's your output. This is your input. So your input was -0.5. Your output was -2. And that is documented right here in my table. Okay. Couple more points. This time my input is 0. So I'm right here, inputting 0. What is 1 divided by 0? Please don't say 0. I can hear you. I can hear you on the internet. Don't say it. 1 divided by 0 is undefined. It does not exist. All right, it does not exist. It has no value. If you put it into your calculator, it will give you an error message. Right? Some fancy calculators will actually say undefined or DNE. Others will just give you an E, right? An E for error. Right there, just the E in DNE. All right. So I want you to either put an E for error, or I want you to put a DNE. Put something to indicate that it does not exist. It's a vacuous, it's a void. I'm going to represent it on my graph as a hole in the graph, a singularity. All right. We're almost done. A couple more points. Let's plug in 1/2 for x. 1 divided by 1/2. That's 1 divided by 1/2. That's 1 times 2/1, which is 1 times 2 divided by 1. That's a long way to say 2. And I hope you see why the family is called the reciprocal family. Look, 1 divided by 1/2 becomes 2. These numbers are called reciprocals. The reciprocal of 2 is 1/2. The reciprocal of 1/2 is 2. They are reciprocals of each other. And so in my table, when x is 1/2, y is 2. When x is 1, y is 1. And when x is 2, y is 1/2, or I'm indicating 1/2 with a decimal, 0.5. All right, we are almost ready to draw the graph. As I mentioned earlier in this presentation, generally I make each block 1 unit, all right, generally. But this is a very special example. And so I'm going to make each block 1/2 a unit so that you can see the decimals and the fractions. So each block is going to be 1/2 a unit. So this is going to be 1, and that's going to be 2. And that gives me space for my fractions. This is going to be 1. This is going to be 2. In hindsight, I kind of wish I would have done this for all of the examples. I did consider it, but then there's a price to pay for doing this. Well, there's a benefit and then there's a consequence. The benefit is you can draw decimals and fractions. There's another benefit. Notice that the 1s and the 2s and the -1s and the -2 are not so clustered together. It gives you a little bit of breathing room. So that's the benefit. The consequence is you're going to run out of space really quickly. Look, that would be 3. That would be 4. I'm not even going to label them because I don't need them in my graph. But you see, everything has a cost. So what you gain in space and convenience, you'll lose in representation of values. You won't have as many numbers to work with. But I think this will be enough for this particular graph. All right, I'm going to use my red pen, all right, for the center. The center is a hole. Actually, I have a better red pen. I got a red Sharpie just for this example here. So this center here is a hole. Yeah, because it does not exist. So there's a hole at 0, 0. And then that hole goes infinitely far in both directions. And so the way we represent an infinite hole or an infinite sequence of holes is with a dotted line. So we have 2 dotted lines. And the hole is what's called the asymptotic center. It's the center of these asymptotes. All right, and the dotted lines are called asymptotes. All right, and I did my best with my red Sharpie to illustrate the dotted lines. They're sort of right on top of the axes, which was difficult to do because I did one of them in a red Sharpie and the other one in a black Sharpie. So in hindsight, I might have used a different color, but I already did it. So now we're going to plot the points. All right, -2 and -0.5 is right here in quadrant 3. -1 and -1 is right there, also in quadrant 3. -0.5 and -2 is right there, also in quadrant 3. Connect those 3 dots with a curve. And I usually put little arrow tips to indicate that the graph is going forever. All right. So you want to make sure that your curve looks like this, right? You want it to get very, very close to the asymptotes. You don't want to do this. All right, don't do this. That's bad. You don't want to do that. What you want to do is get very, very close to the asymptotes like that. All right. And again, when you're doing this in your homework or doing this, with a mouse, it'll hug it for you. When you're doing it on paper, you need to make sure you get really close to that asymptote. All right, and now let's do the final 3 points. They're all up here in quadrant 1. So I have 1/2 and 2 right there. So x is 1/2, right? Halfway between 0 and 1. Y is 2. I got 1, 1. Both x and y are equal to 1. And then I've got 2, 1/2 right here. And again, curve it out and hug the asymptotes. Curve it out and hug the asymptotes like that. And there you go. That's your last function, the reciprocal function. Normally I would ask if there's any questions. You can email me your questions, or you can comment on my YouTube channel, and I'll get it in my email one way or another. Or if you're in my in-person class, you can ask me in class. I'm going to answer the domains and ranges, and then we will be done with this session. So the domain is the set of all x such that x is not equal to 0. So I like to actually note that right here. X is not equal to 0. And then for the range, it's the same as the domain, but you have to switch the variables to y. The set of all y is such that y is not equal to 0. Sometimes I like to note that here. Next to the DNE, I like to put y is not equal to 0. All right. Again, these little notations are just to remind me that that's an asymptote and not a point on the graph. The graph never actually touches the asymptotes. It just gets very close to the asymptotes without touching them. And then finally, your interval notation would be -∞, 0, parenthesis, union, 0, infinity. And the range is the same thing. -∞, 0, parenthesis, union, parentheses, 0, infinity. And there you have it, my internet friends, my students. Whether you're in my in-person class or my online class, I hope you enjoyed this presentation of the catalog of functions. And keep in mind, there are hundreds, if not thousands of functions, possibly even millions of functions. In algebra, it's usually, maybe 10 at the most. I've seen catalogs that have up to 12 functions, but I picked my favorite 6. And so if they're my favorites, I hope they're your favorites too. And until we see each other again, I'm Dr. Jordan, and I'll see you on the internet.